Hey everybody, and welcome back to Calc 3 Online. So today we're going to talk about doing double integrals over general regions instead of just rectangular regions. To start off, though, I want to talk just about like a concept question actually related to this from Calc 1. So in Calc 1, the way you should, if you see this ever, the way you should really think of that, if you really do the integral out, right, you would just stick an x and then you'd evaluate it from a to b, and so you would end up with b minus a. But conceptually what that is, right, is just the length of the interval between basically a and b. And it is truly a one-dimensional thing. That's the important part there I really want to make sure you see. So if you use that idea, the conceptual meaning of something like this, a double integral over some region D of just dA, the area element, would literally just be, first off, it's a 2D thing, right? Because if you see this without a variable in there, it's just a 1D thing. It's just b minus a. And here it is just a 2D thing. And specifically, it's just the area of D, whatever D is, right? And that kind of idea will actually come in later. There'll be some stuff down the road that's going to kind of help us, like if you have that concept in mind, basically. All right, so a lot of what you run into with double, triple integrals are not just like rectangular regions, and so you have to know how to deal with them. So these are just some different examples of things you could run into for, basically what these are these are like the dA, what you're seeing down in the XY plane. And there's actually a technical term for the difference between these. They either call them type 1 or type 2 area elements. And type 1 are ones that you would want to integrate vertically first, and then do left and right after. Whereas type 2, you would do left and right first, and then up and down afterwards. So the reason is that you can describe like this these two curves here as like, some sort of y equals some function of x. And then these on the endpoints are just constants, right? They're just specifically a and b. And so you always want to end, like your outermost integral should be the constant ones. And if you're doing your inner integrals, those can actually have bounds which are functions like this. Like I could have a lower bound be this g1 and an upper bound be g2. And then that could be my inner function. My inner integral, and then my outer integral can just be constants, and so then I can do my double integral and actually get a number out for the the volume, under the surface and over this region D. So if you kind of keep that in mind, just basically your outer integral can't have a function in the bounds, but your inner one could. That's kind of going to help you tell if it's type 1 or type 2. And so in terms of dy and dx, if you do a type 1, you're doing a change in y first, then x. So type 1 is a dy dx integral, whereas the other one is a change in x first, then y. So it's a dx, then a dy. Things like this are a good example to see too. So if you think about this one, you can either think of it as going from left to right, so that would be like type 2, I guess. Or you can think of it as going from the blue one up to this orange one, and that would be like a type 1. So that's type 1, that's type 2. And so sometimes you get things like this, which are simultaneously type 1 and 2. And there's going to be things like type 3 when we get to triple integrals. And it is good to actually know these two terms because I will definitely be like saying them at times. I'll just be like, so now we're going to integrate over this type 1 region and blah, blah, blah. So you definitely want to know the difference between those. All right. I want to integrate this double integral. I want to solve this thing. And D is the region that's formed by the intersection of 2y equals x equals 0, and y equals 1. So what I would do first is I would just go ahead and graph that region. All right. So if I think I can squeeze it in right here. If I sketch all this out, so this, it's probably easier to just think of it this way. So this is going to be x, this is going to be y. So we have x equals 0, which is, maybe I'll color code some of this. X equals 0 is that, right? Y equals 1 is that, right? And then x over 2, right? If I tick some of this off, so this is 1, 2, 3. If I plug in 2 right here, right, for x, I would have y equals 1. So the point of intersection with this one, with the yellow line, would be that. So, and we know it has slope like that. So the region that I'm integrating over is basically that triangle in there. That's what I'm integrating over. And that triangle, you can think of it honestly as a type 1 or type 2. It's one that could kind of be thought of as going vertically, like purple to yellow, and that would be type 1. Or you can go red to purple, and that would be type 2. Okay? So let's set up a type 1. So we're going to do it with, one of the things that you might want to think about is which one is easier sometimes. And so if you set it up as a type, 1, let's just say, okay, we're going to go from a function in x here in purple up to just a constant. And if we set it up as a type 2, we go from a constant, x equals 0, over to a function of x. And in this case, both of them have a function of x in there somewhere. So it's kind of doesn't matter which one you do, but you have to think about that sometimes because you might be able to save yourself some messy algebra if you set it up a specific way. So don't just assume that if it's type 1 or type 2, they're both equally difficult. One might be easier, and you just got to kind of think about how to set it up and what's going to happen when you start to integrate it. So I'm going to set up as type 1. In this case, it honestly doesn't matter too much. So basically, I'm integrating x squared e to the xy. And I guess another reason I would do type 1 here is if you look at the function, right, it's a much harder thing to do dx first versus dy, so that's another thing to take into account. And actually here, that's the more important thing, because this is just a function of y and this, then I don't have to, this x squared is constant. I would rather integrate with respect to y than x. So that's just another reason. All right, so if I'm doing dy then x, okay, I would use this as my lower bound, right? So my dy is x over 2 on the bottom, and then 1 on the top, right? This one up here. If I was going to do dx, I would have to use 2y as my, actually 2y would be my upper bound, because x equals 0 would be my lower bound, and then I'd go over to 2y over here. And then in terms of x, right, I'm going from 0 to 2, right? That's my x bounds, so 0 to 2. So that's my integral, right? And when you do the integral with, because the first one you're just going to really have to think about e to the xy. X is constant, right? So the same way you do the integral of e to the 2x dx or something, and you can just do, e to the 2x, but then you divide by 2. You divide by the constant in there. It's the same kind of thing, except the constant is an x. And so we would do 0 to 2, and then we'd have x squared e to the xy over x, right? And then we're going to evaluate from x over 2 to 1, and then dx. And you can truly just cancel one of these. And so now I'm integrating 0 to 2, x e to the xy, and I'm going to plug in x over 2 and 1 for y. If you do that, okay, you're going to get so you're going to get, let's see, so you're going to get x e to the x when you plug in 1, and then minus x e to the x squared over 2. Yeah, when you plug in x over 2, and then dx. And basically I would split these two up, and both of them are like classic parts problems. So you want to pick u always to be the thing that as you take derivatives with it, it disappears. So I'm going to try to color code this. So I'm going to do this integral first. So if I just let u equal x, du equals dx, right? And then dv is going to equal everything else, e to the x dx. And so the integral of that is just e to the x. And so then this first one is going to be, here, we'll do it down here. Just running out of room. So we'll have uv, so x e to the x, and then we're going to evaluate that 0 to 2, minus the integral 0 to 2 of e to the x dx. And let's see, if you do that out, you're going to get e squared plus 1. Yeah. Just because there's like 2 e squareds in there, and then you're minusing the e squared here. So you're going to have e squared, and the 1's coming out of here. So that's the first one. And then this one, I'm going to let u equal x again. Du is dx. dv is everything else, which is... where was I here? So we'll just do e to the x squared over 2 dx. And then v would be... Actually, I just realized we could do this one better. We could do this one with substitution, actually. So that's what we're going to do. It's going to be easier. You can do substitution because you can pick u to be this thing, right? And then the derivative... you're going to be able to, when you take the derivative of this, you can get the x dx. So I'm basically just going to do u sub. So let u equal x squared over 2, and then du is just, it's just going to be x dx. So that's in there. So then I'm going to do the negative on the outside. So the negative integral of x e to the x squared over 2 dx is going to become negative integral e to the u du. And that's really nice because that's just negative e to the u. And I'm evaluating it when u is x squared over 2. And so I get negative e to the x squared over 2, right? And I want that when it's 0 to 2. And so that one is going to be negative e squared minus 1. And so then if you do e squared plus 1, let's see, where can I put the final answer here? So I don't know if I can fit it in. All right, we're just going to do this and this, right? So I'm just combining this and this. These are my two parts, right? So this final thing, you have e squared, right, minus an e squared, and then you have a plus 1, and then if you distribute the negative, you have another plus 1. So really, that is a very weird way to write the number 2. That's what it is. So some of the really important things I just want you to see there are like how I went about drawing the region and figuring out how to set it up. That's always like the most tricky part. And then a lot of it really just feels like kind of Calc 1 integral stuff here. But the setup is definitely the most important part. All right. So kind of in terms of setup, that's what this question's kind of getting at. So this is a two-dimensional problem, really, right? This is truly just an area problem. And I want to start off by just sketching the region that you see there. So when I have something like this, right, this you want to think of as like x equals y squared and x equals y. And then y runs from 0 to 1. So here's my 0, here's my 1. And x equals y squared, right, is really just like really just like a parabola that opens up in x, right? So here, let's color code this. So this one I'll do in purple. So, it really looks like this, and really there's this part too, but we don't need it because we know y cuts off at 0. So that's like, and maybe I'll, oops. Go a little bit more like that. Okay. This picture's not the best. Okay. Just because now I know that's 1. So, and then y equals x is not bad, right? That's just like that. And so the region that we're basically getting from that integral is that like kind of, I don't know what that looks like, some sort of curved region in there. But so this is something that you, again, actually could think of it as type 1 or type 2. So you either can go as a type 1, it would be red up to purple. All right, purple. And as a type 2, it would be a purple over to red. Okay, so you can either think of it as up and down or left and right. And then just want to go ahead and solve the integral. So the first integral, all we really have to do is just do like y minus y squared, right? And this is going to now be dy. So that's honestly the dx integral. And then you just go and do a one-dimensional integral like this, which is the area under the curve y minus y squared, which is why you get an area problem out of a double integral. So you just get y squared over 2 minus y cubed over 3, and then you're going to go 0 to 1. The zeros are nice, right, because they just cancel, and then you have a half minus a third, which is a 6, and that's it, okay? But again, the important stuff here is the setup. So I want to make sure that you can see something like this and understand what it looks like in a picture, because this is going to be a really important part of a lot of these problems. All right. Just want to do another one of these because the more examples you see right now, the better. They're definitely going to get harder as we go. So I'm going to find the volume of a tetrahedron, which is just like a four-sided pyramid, bounded by the planes x plus 2y plus z equals 2, x equals 2y, and x equals 0, and z equals 0. So the idea here is to basically do, so I would think of it as we want to do a double integral with z equals something, right? So this is going to be z equals 2 minus x minus 2y. So this is basically my kind of upper bounded surface, right? And I'm going to find the volume in these like rectangular prisms under that and above z equals 0. And I'll do that with a double integral. So we need to figure out what our 2D region is that we're integrating over. And so we know we have x equals 2y and x equals 0. X equals 0, right, is just this line right here. And then x equals 2y is, if I'm drawing it this way, it might be easier to think of it as x over 2 equals y. And that, right, just looks like, so we'll do that. Looks like that. And then at first it looks kind of tricky because we're like, where's my other bound going to come from? But that's what this is going to do for you. So really, that plane is sticking like up out of the page above this 2D region, but we can also sort of simulate that by just letting like z equals 0, right? And then thinking of what 0 equals 2 minus x minus 2y is. And what we're just doing there, right, is we're just thinking about it in the plane z equals 0. And so if you just, let's solve this for y, you would just get 1 minus x over 2. And so that bound has y is up to 1, and then it's going to go here and then here. And so we get that, okay? And so it's a little hard to see, but basically this is my triangle that I'm integrating over, and that really is meeting at 1, this is at 1/2, this is at 1, and this is at 0. And so that should be enough to go ahead and do this integral. We already have everything in terms of y right now. So I think when I set this thing up, I'm just going to set it up as a double integral of 2 minus x minus 2y, and then do a dy dx. So do a type 1. And, in a type 1, my lower bound is the orange one. So that's going to be, it's going to be x over 2. And my upper bound is the red one, 1 minus x over 2. And then, that was me going vertical. And then left and right, I need to go from 0 to 1. So I'm just going to do 0 and 1. And that's usually the hardest part. And then it's just a lot of, bookkeeping. So I'm going to kind of do this part out a little bit quicker here. So the first dy integral, you would get this. And, that's me also going and plugging in my bounds, basically. So, this is kind of my my first chunk that I plugged in with this, and then I do minus the other part with x over 2. And then, you just crank out all this algebra, multiply this out, square this thing. And if you do that, you could simplify it down to 0, 1, x squared minus 2x plus 1 dx, which is much nicer. And you would get x cubed over 3 minus x squared plus x 0 to 1 equals a third. That's it. But definitely this part, again, is the most important part because it's by far the trickiest, kind of most new part to these problems. All right, one more. So another thing that we're going to see a lot of times is sometimes areas just are not type 1 or 2, but parts of them are type 1 or 2. And since what we're doing here is additive, like you can just take, an integral over, if you have some region A to B, you can go to A and then halfway, do that integral, and then go halfway again to B, and that would be the same thing, right? You can add up those area chunks, basically. You can do that with double integrals, and you can add up different volume chunks, basically. So when I look at this weird region, it's not type 1 or 2, because, I can't just, there's no function, it's piecewise, right? That goes from, like, say, this left side over to this. Likewise, there's no nice function that goes from here up to, like, something up here or whatever. So you have to do it in pieces. Technically, you can do it in 3 pieces. You could do one in quadrant 1. So you could think of it as just this chunk, do that setup, and then you could do like quadrant 2, that part, and then quadrant 3, that part. Or you could even do it a little bit better, because you can combine the red and green into one big chunk as well. So that is actually how I'm going to go about doing it. And so I am going to set this thing up. I'm not probably going to solve it out because it's kind of a straightforward integral, but I just want to go through the setup part. So the functions are given here. So this this part right here is the quadratic quantity x plus 2 squared. This right here is the function y minus a 16th y cubed equals x. That's what this whole thing is. And then this is, of course, y equals -4. This is x equals -2. That's all of them. And so I'm going to do a type 2 up here, all right, in green. And so we're going to do a type 2, and then purple is going to be type, type 2 also. Okay, so for my type 1, so if you, here actually before I get into that, so if I'm going to do a type 2, right, type 2s are dx then dy. So this one's nice. It's already set up as an x equals, but this one's not. So I have to do that here. And, if you go through the algebra really quick, I would basically square root both sides, but you have both plus and minus square root of y equals x plus 2 there. And then both plus and minus square root of y minus 2 would equal x. And if you think back to like algebra 1 or 2 or whenever you learn this, just remember that, for these kind of things, like the positive square root, the positive square root is going to be actually that side for an x equals 1. And then the, we'll do it like red or orange, I guess. So this side would be the negative square root 1 for an x equals. This is only for x equals stuff. So x equals. It's the other way around, right, for y equals stuff. So, so I'm going to take the positive square root of y minus 2 equals x. And so my green integral is going to be, so I'm going to have 2x plus 5y in there. That's my function right up here. And then I'm doing dx plus dy. Nope. I'm doing dx dy. And then dx is running from square root of y minus 2, right, up to, or over to, I should say, y minus a 16th y cubed. And then, so I just went from here, this curve, over here. And now I'm going to go bottom up. So I'm going to go do 0 up to 4. That's the upper half, basically. And then the bottom half, this purple part, would look like this. And that's just because I'm going from here, right, -2, over to this curve, which is part of this y minus 1/16 y cubed function. And then I go bottom -4 up now to 0 as the upper bound. And so if you did that whole thing out, that's what this integral over this d region would be.